So now we're going to look at some properties of continuous random variables. The good news here is that lots and lots of the things we already know about discrete random variables are going to follow through exactly for continuous random variables. The main differences are, wherever we had a probability mass function before, we now replace that by a probability density function. And then before, whenever we were summing the probability mass function, we instead integrate the probability density function. So most of the things, if you just write down things you know about discrete random variables, if you swap PMF for PDF and sum for integral, almost everything follows through. So I made a list of these in the notes, and I'm just going to basically go through the notes for the start of this video. So I've got two columns here. On the left-hand column, things we already know about discrete random variables. And in the right-hand column, we're translating those into continuous random variables. So if we look at the first row, we had that for a discrete random variable, we have its probability mass function, which represents the probability of getting exactly x. But we know that for continuous random variables, we instead have a probability density function, which tells us like how much intensity of probability is there around x. So for discrete random variables, we knew that the probability mass function was always non-negative, and the same is true for a probability density function. It's also always non-negative. For a probability mass function, we knew it had to sum up to 1, because that represents the probability of anything happening. And the same is true for probability density functions, that they have to integrate to 1. If you think the integral from minus infinity to plus infinity gives us the probability of getting any of the real numbers, and so that must be everything, probability of omega, and so that will be 1. You'll remember that for discrete random variables, we talked about the cumulative distribution function, which is the probability that the random variable is at most some value x. And we talked about how you could find that by summing up the probability mass function up to x. So for continuous random variables, this continues the same way. If we want the probability x is at most x, we have to integrate the cumulative distribution function up to x. Slightly annoyingly, there's a typo on my slide here. The bottom limit of that integral should be minus infinity, not 0. By the time you read this in your notes, that will be correct. But in the notes, it correctly says that bottom limit is minus infinity up to x to get the probability of being less than or equal to x. We had the expectation for discrete random variables, right? And we had the formula for it, which was the sum of x times the probability mass function of x. And so here we have, for continuous random variables, we have the same thing, except it's no longer a sum, it's an integral, and it's no longer the probability mass function, it's the probability density function. So the expectation is the integral from minus infinity to plus infinity of x times the probability density function of x. For discrete random variables, we had the law of the unconscious statistician to tell us how to find the expectation of a function. And it was sum up that function times the probability mass function. So here, to get the expectation of a function for a continuous random variable, we integrate the function times the probability density function. And then the last two things are things that follow through exactly, which is linearity of expectation works exactly the same way, and the variance has exactly the same definition and the same properties for the variance. So those are all properties that we knew for discrete random variables that transfer over for continuous random variables as long as we swap the probability mass function for the probability density function and sums for integrals. There is one property actually that doesn't follow through. Because the probability mass function always represented an actual probability, that meant the probability mass function was always less than or equal to 1. That's not true for a probability density function, because a probability density function doesn't directly measure probability. It only measures probability once you integrate it. So a probability density function can be greater than 1. Obviously not for too long, because otherwise the integral would end up being bigger than 1. But there's nothing to stop a probability density function being bigger than 1. So you've got to be careful. That's the one property that actually doesn't follow through. So what I'd like to do is to go back to our previous examples of probability density functions from the past subsection and see if we can check the properties we just talked about. So you'll remember that we talked about the continuous uniform, which was f of x equals 1 for 0 less than x less than 1 and 0 otherwise. So, is it true that f of x is greater than or equal to 0 everywhere? Yes, it is. It's either 1 or 0. Either way, that's fine. So, tick for that property. We said that the integral was equal to 1, didn't we? The integral from minus infinity to infinity of f of x dx. Well, what is that here? Well, the probability density function is only non-zero between 0 and 1. So for this random variable, we only have to consider between 0 and 1, because the probability density function is 0 or else. So this is the integral between 0 and 1. The value of the probability density function there is 1. The x, so 1 integrates to x, 1 minus 0, equals 1. So that's correct as well. The integral of the probability density function is indeed 1. Third thing we talked about was the CDF, the cumulative distribution function. And we said that that was the integral from minus infinity to x of x dx. Now we're going to have to treat this a bit differently depending on what the values of x are. Right? Because if f of x, if x is less than or equal to, is less than 0, well, this random variable only took values between 0 and 1. So if x is 0, the probability that this random number is less than minus 2 is 0. It's always between 0 and 1, so it can't possibly be less than minus 2. For the same reason, because the value is always between 0 and 1, the probability of it being less than or equal to something bigger than 1 is 1. That's certain. It's definitely going to be less than 7, because it's going to be between 0 and 1. So it's just the bit between 0 and 1 that we actually have to worry about. So let's assume x is between 0 and 1. And this is going to be the integral from, well, again, the probability density function is 0 on all the negative numbers, so we can just start it from 0. And then the value of the probability density function is 1. The x, so that's before, that's x. I shouldn't use x there, should I? It's bad notation. I should use a different letter. I just didn't want to use x twice. X is in the limits of the integral, so it ought not be inside the integral as well. Between 0 and x, that gives us x. So that's that cumulative density distribution function. We kind of plot that, it looks like, well, it's 0 down here, then it's x, then it's 1. So that tells us the probability of being less than or equal to that number. We also looked at the expectation, didn't we? We said that the expectation of x was the integral between minus infinity and infinity of f of x dx. This time x isn't in the limits, so we're okay to use it inside the integral. Well, again, sorry, I'm missing an x there, aren't I? Again, the probability density function is 0 except between 0 and 1. So it's only between 0 and 1 we need to worry about for this random variable. The PDF, well, the PDF is just 1 here, isn't it? So there's nothing to write. That's the integral between 0 and 1 of x dx. You integrate that. Here, half x squared between 0 and 1. That's a half times 1 squared. Minus a half times 0 squared equals a half. So the expected value is dead in the middle of that interval, as perhaps you expected. And we also have the variance, which is the expected value of x squared minus the expected value squared. So to find the expected value of x squared, we use the law of the unconscious statistician. This is the integral between minus infinity and infinity of x squared of x dx. But for this random variable, we only need to look between 0 and 1, and f of x is equal to 1. So that's going to be 1/3 x cubed between 0 and 1. That's going to come out as a third. So the variance of x is equal to a third minus mu, which is a half squared. I believe that comes out as a 12th for the variance, using the fact that we knew the expectation was a half. So that was me trying to quickly run through all those properties for our continuous uniform distribution. But you can see it's all coming down to integrating probability density functions over the areas where they're non-zero. We did have another example, didn't we, which was this triangular distribution where f of y was either y or 2 minus y, depending on whether you were between 0 and 1 or 1 and 2, 0 otherwise. That was this kind of triangular shape we had up here. I'm not going to run through all those examples again, but let's just do a couple of them. Let's do the CDF. So as a reminder, f of y is the integral from minus infinity up to y of, again, because y is in the limit, I don't want to use that inside the integral as well, so let me just use z, but any letter's fine. This, again, has, because this only takes values between 0 and 2, this means if y is less than 0, f of y is 0. If y is greater than 2, f of y equals 1. And so it's only the bit in between we need to worry about. But note that f of y is defined differently for y between 0 and 1 and y between 0 and 2. So we should probably treat those differently for the CDF as well. So 0 less than or equal to y less than or equal to 1, less than or equal to 2. So let's do the y between 0 and 1 first. It's wrong in lots of ways. So if y is between 0 and 1, we don't have to worry about up until 0 because that's all 0. So we've just got an integral between 0 and y z dz, because that's this here. But now we've replaced y's with z's just inside this integral, just so we're not naughtily reusing letters. So again, that's a half z squared between 0 and y, which comes out as a half y squared. What about if y is between 1 and 2? Then, well, up to 0 is nothing to worry about. And we've got all of between 0 and 1, z dz. Then also from 1 up to y, where it's 2 minus z dz. This bit over here, half z squared between 0 and 1. This bit here, 2z minus half z squared between 1 and y. That comes out as a half. This comes out as 2y minus a half y squared minus 3 over 2. So it all comes out as 2y minus a half y squared minus 1. I've calculated that correctly. I'm just going to check my notes that it agrees. Yes, it does. So up here it's 2y minus a half y squared minus 1. And you can see a graph of that in the notes, what that CDF looks like. Like, that expression looks like quite a lot of mess with like 4 different cases, but actually the picture of it looks rather pleasant if you just scroll down and look at that in the notes. Finally, let's also do the expectation as well. The expected value of y, equal from minus infinity to infinity, y f of y dy. So again, it's 0 except between 0 and 2, but then it is different between 0 and 1 and between 1 and 2. So let's split it up as between 0 and 1, we've got y. F of y is y there, so that becomes y squared dy. Between 1 and 2, it's y. F of y is 2 minus y there, dy. This is 1/3 y cubed from 0 to 1. If you expand out the brackets, the 2y becomes y squared. The y squared becomes 1/3 y cubed, and that's between 1 and 2. And I did calculate what this was earlier, and rather conveniently, it comes out as 1. The expected value of y is 1. So those were just a few quick examples of working with probability density functions and about how it's all about integrating them to get cumulative distribution functions or expectations or whatever. But the basic ideas are the same as in discrete random variables, but we've got all these integrals of probability density functions hanging around instead.